So first, I would like to thank John for organizing this, also Megan for inviting me, and the math department for having me here. I've seen that they do a lot of cool stuff in these seminars. Been able to see thanks to that they recorded. So thanks a lot for having me here. So the idea of what we are going to be doing today is I'll read you two quotes that I have, and then I'll try to explain why I have them. So this is from a book that I'm reading these days. It's a Russian professor that is trying to teach math in a fun way to kids that are 3 years old or 4 years old. So you can imagine how adventurous that is. And he says, the first quote is, if I taught kids anything at all, it was the idea that they should experience their world with openness and interest. And the second quote is when he's referring to how you're teaching to them. He's saying, you should use all your adult authority not to impose correct answers, but to convince a child of the importance of his own reasoning and intellectual efforts. And this is by Alexander Svonkin. I think that's how you pronounce it. So the idea of today's seminar is just to remind us of something that sometimes is not talked too much about mathematics. Math can be, and part of it is a way of looking to the world in a really open way. It's about asking questions. It's about being curious about what is around you. It's about being able to see structures and be like, or patterns, why is that happening? So that's the idea of today. We are going to be talking about some mosaics, some angles, and some polygons, as the title said. So let's start with the first thing. One of the most basic shapes, and probably the most basic polygon, is a triangle. Who can tell me words or things that you remember about triangles? Things that are pretty popular about triangles. Anyone? How many sides? 3 sides, right? 3 sides. What else?
Sum of the angles is 180 degrees.
Sum of angles is 180 degrees. And you arrived pretty fast to the one that I wanted you to arrive, so thanks a lot. So yeah, there are 3 angles, 3 sides, and something that we say a lot, and that is used a lot in geometry, is that these 3 angles, alpha plus beta plus gamma, should be equal to 180 degrees, okay? There are many, many proofs of that, many, many ways of convincing yourself that that is true, but I'm going to try to convince you otherwise today. Now, be very, very observant, because then if I say something that is wrong, you get to say, hey, Javier, you are wrong. And that's pretty satisfying, I think. So I need my first volunteer of the night, or of the evening. I need the first volunteer. It's nothing difficult. You'll just have to be here in this lovely chair and sit down and go like this. Woo! That's all. I need just one volunteer.
I have to go teach, otherwise I will do it.
Okay. I'll do it. Thank you. Thank you so much. Right. What's your name?
Melanie.
Melanie. Thanks, Melanie. Okay.
I can sit. All right.
And you get to play too, not only sit. Right. Okay. So as you can see, there is a triangle in the center of the room, right? So what I'm going to ask Melanie is to help me keep track of what angles I am turning. Okay, so what I'm going to do is I'm going to walk on the triangle, actually on the sides of the triangle, And maybe you can help me just record how much I am turning. So can we start looking, facing the same direction? Maybe if you want here, so that, yeah, maybe we start facing the same direction. So I start walking, right? And then I turn here, right? So your turn there, thank you. Then I keep walking, and then I turn, right? Here, and then I keep walking, and then I turn to be back to my original position, right? So you are back, right? Now, can you tell me how much did you turn?
I get your point. 360 degrees.
360 degrees. Okay, so I turn 360 degrees, but I feel like you're already going to tell me you are wrong. So let me pose the question, and then you get to tell me. So I'll just do it again. Can we do it again so that everyone sees? So I go here, right? I turn. I go here, then I turn, and I go here, and then I turn, and we are back, right? And what happened is that she went around 360, right? So my claim with this argument, my claim is that the angles are not going to add up 180. My claim is that they are going to add up 360. Now, I'll give you just like 30 seconds to think on your own. Am I right? Am I wrong? What is going on here? Just 30 seconds. Give me a...
You have a direction, right?
Say that again.
When you start, you're facing that line, right?
Mm-hmm.
And you went there, and then you turn to face this line.
Correct.
And then you turn to face that line, right? And then you move back. So I feel like you're right, but in a way that you turned extra to make it 360.
Okay, so you feel like this last turn...
Yeah, every time you have to turn extra to get to 360.
Okay, so you what's your name?
Lena.
Lena. So Lena says, Javier, you're turning more than what you need. Right? Okay. Why are you saying that I'm turning more than what I need? Because I'm going here, and then I just turn enough.
No, you don't need to turn.
Okay, what do I do?
Yes, you can turn that.
Okay, thank you. There you go.
Go. Yeah,
And I keep going, right?
keep going.
So
Yep.
I'll just follow your direction. You tell me what to do. Can I turn?
When you turn that, you are turning on this angle.
I like that. I like that.
So that's how it gets me.
So you're telling me I'm cheating?
But you are, because, okay, so can I?
You can come, yeah, of course.
Sorry.
Yeah, please do.
I figured out what you did.
Okay, that's great. Because you get to call me you're wrong. And I love that.
Can I use this?
You can. It's all yours.
Okay, so this is part you add up. And this is a part
Maybe can you use one that is actually working?
Yeah, so you add up this part, and this part to make it work.
That's awesome. Thanks a lot. Let me get everyone in the same page. That's pretty cool. Thanks a lot for your help. That was
You're
awesome.
very welcome.
Thank you. So there's a couple of points that I have with this, but Lena, is that your name?
Yes.
Lena made a really excellent point. Let me just extend this a little bit so that we can see it. So the point that Lena is making is the following, is when she's saying, look, when you are turning at each vertex, you are not actually turning this one that is inside. right? You're turning the outside. So let's look at it. Look at, I don't know if everyone can see. If not, you can stand up so that you can see. My foot is right here facing in the same direction as the side. And when I turn, look at the angle and the movement that my foot is going to do. It's going to go here, right? So it's going from here to here. So as Lina was saying is, as I am turning, my foot is facing this direction, and then it ends up here, right? And same thing is going to happen once I get here. Instead of turning this, what I'm doing is my foot is facing this direction, and when I turn, I end up here.
That one I was wrong.
And this one, I am turning not this way, but I'm facing this direction, and then I end up this direction, so I'm turning this way. Right? And that's what is happening, right? I come here, boom, I come here, boom, I come here, boom, right? And so this is something really important in math. And in general, that's another thing that math can teach us. And that's that we need to be precise in what we say. So let's see what we have gotten so far, right? What we have gotten really is that the sum of this angle plus this angle plus this angle is 360, okay? Now, let's give them names so that we are all on the same page. These angles that we have been calling outside angles are usually called external angles. And the ones that are inside, you can guess, they are called internal angles. Okay? So, so to be precise on what we have shown with this exercise is that the sum of the external angles of a triangle is 360. Okay? So that's what we have shown. Now, let's go back to what we had at the beginning, which is the sum of angles is 180. Now, what can you tell me about the relationship between the external angle and the internal angle? They add up to 180 degrees. Why is that?
Because like the line is a flat line, and every flat line is 180.
That's awesome. What's your name?
Kyle.
Kyle. So what Kyle is saying is, look at this line, and look, here is this internal angle and this external angle, and they form the line, which is 180, right? Same thing happens here. This one plus this one gives me a line, which is 180, and same thing happens here. So the other thing that we have shown, thanks to Kyle's argument, is that an internal angle plus external angle add up to 180, right? And these have to be at the same vertex. Okay, that's pretty good. Now, let's take these two facts together just to show this, okay? So let's look at this. So if you allow me, I'll call this external angle A, this external angle B, and this external angle, this one, C, okay? So basically, what I know is that alpha plus A, thanks again to what Kyle said, is 180. Then beta plus B is 180. And then gamma plus C is equal to 180. Okay? So if I add up these three things, what I get is alpha plus beta plus gamma plus A plus B plus C equals to 3 times 180, which I am not completely sure how much it is, but 450?
No, 550, 540.
540, thank you. 540. But let's look at this expression here. A plus B plus C. Can we say anything about A plus B plus C? What is A and B and C? They are the external angles, right? And we just said that the sum of them is 360. So what we end up having is that alpha plus beta plus gamma plus A plus 360 is equals to 340. And then I can take this to the other side, and I get alpha plus beta plus gamma equals to 180. And this was the other one that we started with, that we wanted to have at the very beginning, right? So, this is a really nice argument, because if you see, we are using kind of like the physical world to prove something in geometry. There's a book by Uspensky that is called Applications of Mechanics to Mathematics. And the idea is to use things from the physical world to prove things about mathematics, which is super interesting, because we usually go the other way around. We use math to prove things about mechanics, but this is coming back. So we have that the externals, the sum of external angles in a triangle is 360. We have that the internal plus external is 180, and we have that the sum of internal angles in a triangle is 180. Okay. Now, let me ask you one more thing. Was it any special that this was a triangle? So say that now, instead of a triangle, I decide to add 2 sides. And I come and I do something like this. Forget about this line in the center. Actually, since I want to forget about it, I'll just take it. So there's that. And then what if I just do this? And I'll just extend this one here. So for the people that can see, I guess I'll do it with. For the people that can see, how many sides does my new polygon have? For the people that can see? 5-ish. 5-ish. You want it to be perfect, so I give that to you. So let's count this 1, 2, 3, 4, and 5, right? So my question is, was it any special that I had a triangle when I asked Melanie to be rotating in the chair? So let's look at it really fast. Sang, would you mind to just go there and let's do this really fast. So let's look at what happens here, okay? So can we start in the same position, facing the same way? Yeah, so I'm here, right? I go, I turn, right? I go, I turn again. You went too far. So I go, and I turn, and you are there, and I go, and I turn again, and then I go, and I turn again, right? So how much did Sang turn? 360, right? Was it any special that it was something with 5 sides, or 3 sides, or 10 sides? It doesn't matter, right? Thanks a lot, Sang. Thanks so much. So basically, this idea tells us that tells us more, but let's say that in a, I'll add a word just to be precise, but in a convex polygon, I'll tell you what this I mean by this convex polygon. The sum of, how should I say this? The sum of what? Exterior angles or external, actually exterior or external angles. Now that you say it, I think it's exterior angles that is used, right? But I guess I'm calling them external today. So external angles is 360, right? So that's pretty useful. And what do I mean by convex? I just mean that it will not have things that go inside, like cuts that go inside. Because if it has cuts that go inside, it's a little bit different. But still, we could conclude the same thing. But I'm going to just focus on this kind of polygon today. So I have again that the sum of external angles is 360, right? So I could do something similar, right? Say that my polygon has n sides or n angles, right? Now, who remembers what a regular polygon is? Who can tell me what a regular polygon?
Equal sides, equal angles.
Equal sides, equal angles. I love that. So regular polygon is a polygon that has equal sides and equal angles. Examples of that are triangle, in which case equilateral triangle. So if we know that these three are equal, and we know that they should add up to 180, necessarily this has to be 60, 60, and 60, right? Otherwise, since they have to be equal, they need to be 60. Now, in the square, since these have to add up and they have to be equal, they have to add up. I haven't said how much they have to add up, so I don't know. But at least in the triangle, we know that these are 60, 60, and 60, okay? So let's make a small game so that we can determine this and get a table that is going to help us to get us to play here. Okay, so this is the idea now. So say that you have a polygon with n angles. Okay? And so, for example, let's do it with a pentagon. So I have 5 angles. Okay, so let's do the same game that we did with the triangle. I'll call this one alpha, okay, and this one A. I'll call this one beta, and this one B. I'll call this one gamma, and this one C. I'll call this one delta, and this one D. And I call this one epsilon, and this one E. Again, this is internal angle and external angle, right? And what we know, thanks to Kyle's idea, is that, again, alpha plus A is equal to 180. Then beta plus B is equal to 180. And I could write them all down, and I end up with epsilon plus E is equal to 180. Okay? So if I add this up, again, I end up with alpha plus beta plus gamma plus delta plus epsilon, just the internal angles, plus all the sum of the external angles, right? So I get A plus B plus C plus D plus E, right? But in reality, I don't really need to write all that down because I already know what the sum is for external angles, right? I know that this whole thing that is outside is just 360, right? So I end up with an expression that looks like alpha plus beta plus gamma plus delta plus epsilon plus 360. And this should be equal to what? Well, I had on the other side, I had 180 5 times. So I should have 5 times 180. And I don't know, 900? Excellent, 900. Okay. So again, I can play this game. And notice that I can get the sum of the internal angles of a pentagon by subtracting this minus this, right? Okay. So the game is a little bit, can be simplified because when I am in a regular polygon, all these angles are just the same angle. So all of these are alpha. And I get something that these are just all alpha. So I basically get 5 alpha equal to 5 times 180 minus 360, right? So I can find out what alpha is by just saying, OK, alpha is just 5 times 180 minus 360 divided by 5. OK? And I get an expression for this angle. OK, so some shenanigans here, but the important thing is that I can get, this is a formula for the internal angle of a pentagon, okay? Now, using the same ideas, we can come and have an expression in general. This one I'll just write down, but if you follow the same argument, you can get this. And the idea is going to be that if you have n sides, well, you will have, right? You have n sides, and then you have alpha. That's the internal angle, right? And then you'll get n times alpha plus all the external angles. That will give you 360, the sum of those external angles, equals to 180 times n, right? If you're not completely following this, you can believe me, and then when you have more time, you can go and see back what we did. But this is basically the same angle n times, then 360, which is just external, and then 180 times n coming from the n equations that we have at the beginning. Okay? So basically, alpha ends up being equal to 180 n minus 360 and divided by n. And this is my expression for the internal angle of a regular polygon. It's important that it is regular because it simplifies it here. Okay? So fast forward to calculating a bunch of them. And I'll save you some time. I know you want to do it yourself. Pull out the paper and the pencil. But then what happens is that this is the number of sides. And this is the internal angle. And then what I get is that in a regular, and these are all regular polygon, I get 60, 90, 108, 120, 128, 135, 140, 144, 147.27, 150, 152.30, 154.28. I promise I have a point of writing them all down. 157.5, 158.8, and 160. Okay? Could keep going, but I want still the pleasure of calculating the rest for you. Okay? So this is kind of like the first part. We use something physical to prove some mathematics, which is something that can be done in other contexts too. Okay? So we had that beautiful list of angles, of internal angles of regular polygons. Now that we have that, let's talk about mosaics, okay? Because This is something that we can use to do mosaics. Now, John, could you help me? It has a password or something. So while John helps me with that, what do you know about mosaic? What comes to mind when you hear the word mosaics? Anyone? Patterns? What kind of patterns?
Like visual geometric, like linked together in a way that they make one bigger shape.
That's true, yeah, right? You think of shapes put together, and then they make a larger thing, right? What else? What else comes to mind when you think of patterns? Oh, for mosaic, sorry.
They're symmetrical.
Symmetrical. What do you mean by that?
That's what those like I was seeing my life. It's symmetrical, but I don't know why they do that. Probably more beautiful.
Probably beauty. A lot of beauty comes from. Thanks, John. Comes from symmetry, right? So I'm just going to show you what Google says when you type mosaics, right? So look at all these beautiful things, right? Some are more complex than others, I think. But for example, this one is an Islamic geometric pattern. This one is really cool to do. But others, if you see, they are just pieces put together, right? And some features of it is that there's no empty spaces, right? You make them match. Excuse me. Some other features is the coloring. There's a lot of color. And so imagine if we try to study all of the mosaics. Just like it is that right there, it would be really hard, right? Because there are just, you can do whatever. Look, you can do this guy that I don't know how it's called in English, but
Big bird.
Big bird, okay. Perfect. I just saw it in Spanish, so I don't know. This is little bird, I guess. So it would be really hard to classify them because you can just make whatever and make them match, right? So part of mathematics is also, as I said, to be precise and to define your problems so that you can study them, right? So what we are going to focus is on mosaics that can be done. Maybe the easiest thing to do is instead of looking at any kind of mosaic, we just look at mosaics that can be done with regular polygons, right? So what if I write regular polygon? I don't know. Regular polygons. Look, it changes a little bit, right? Look at this one, for example. This one has some hexagons, some squares, some triangles, right? This one has some triangles, hexagons, and some. These are not just regular polygons, right? So I guess I guess you can think of, oh, I could do it with any polygons, but if we want to make our studies simple, maybe we want to start with a simple thing, and that's regular polygons. Okay, so let's just look at this one back here. What is a feature of this mosaic? Some things that you notice about it.
There are no gaps.
There are no gaps. How could we translate there are no gaps in terms of some math? Say that again?
It's complete.
It's complete, okay. Say that again? The angles match up, right? Something that is really important is if you see at each vertex, each of the angles match up, right? There's not an empty space where another shape could go, right? So we can say that mathematically, we can say at each vertex, all the internal angles of the polygons that meet at that vertex will add 360, right? Because if you see this plus this plus this plus this angle is the whole circle, they should add 360. So that's one way of putting in math terms the idea of not empty spaces, right? What is another thing that you notice in this pattern specifically?
They're made of triangles, squares, and
That's correct. That's correct. So hexagons, triangles, squares. Anything in particular about how they are put? I think you were going to say something a moment ago, right?
Yeah.
And we interrupted you. What were you going to say?
It's repetitive,
What do you mean by repetitive?
as in you're having at all the corners, it's the same shapes that are meeting up to make that.
That's perfect. What's your name?
Jen.
Jen. So what Jen is saying is, can you repeat what you just said? I think you said it very good.
That all of the corners that are meeting up are the same for each one.
Right. So let's look at the vertices or the corners, right? Say that I want to describe a corner by saying what kind of pattern I have, right? What kind of polygons I'm putting in it. So for example, say that I take this one, right? So I would say I have a triangle, a square, and a hexagon. Do you guys agree with me? Now, if I write that down in this form, I'll say this again, and I'll write this down, and let's see if it makes sense. I could say again, I have a triangle, then I have a square, then I have a square, and then I have a hexagon. Does that make sense? What I'm just saying is, look, this one, this one, this one, and this one, they are just representing the number of sides of the shape, right? So let's look again at a different vertex. So I was looking at this one. Let's look at something around this corner, for example. At this corner, I have, again, if I start by the triangle, I will start here. And I could say, oh, look, I have a triangle, a square, and a hexagon. So again, I have a triangle, a square, and a hexagon, right? Can someone find a different pattern besides this one? Yes.
The numbers kind of like, they like hit next to each other, like some of the same.
Say it again?
Some of the same numbers like next to each other.
That's correct. So you have some repeating, and they are next to each other, right? Now, can you find a pattern that will, for some reason, have different shapes or in different order?
Yeah.
Yes? Could you tell me which one?
The triangles and
You can come and point here because it's going to be hard. Would you point it at me? Or I'll just move. You tell me where to move. Up, down.
like, it looked like a house. They look like a house.
Looks like a house.
Like they look like houses.
Oh, like these houses?
Yeah.
Okay, so this one.
Yeah.
Let's look at that one. Okay. Sorry. So that one will have a triangle, hexagon, and triangle, and a hexagon. Okay, so that's 3, 6, 3, 6. Okay. That's right. But this is interesting because this one, then you don't have the same pattern in each of the places, right? But you can find the same. So for example, here and here you find the same one. And here you find the same one. And right here, and right here, and right here you find the same one. So it's kind of like you have two kinds of pattern on each vertex, right? Okay. So the last thing that we haven't said, but that this specific mosaic satisfies, is that you don't have things that are shifted, right? So for example, you don't have things that look like this. You don't have things that, here's a polygon, right? And then half of one side is in that side, and half of the other side is this side. Sides match, right? So that's something that we have in that pattern, okay? So here's what I would like us to do in the following, say, 5 minutes. In order to find mosaics, right, the bigger picture, we definitely need to find at least these polygons that will add up to 360, right? Because they are going to be our building blocks. So here's what I would like us to do. Let's try to find as many patterns that will give us 360. And the moment you have one, just raise your hand, and I'll come and I'll listen to you, okay? So if you could pass this to the back so they have, and you guys can take some squares, and I'll give you guys some polygons. Can you pass them around? and you guys can get some squares, and I'll bring you more. Okay? So in the 5 minutes, next 5 minutes, let's try to find as many patterns as we can that will give us this 360 option. So can I have some? So I'll just do this. And you get to play with hexagons and triangles. You guys just have the squares, so.
Yeah, we're working on it.
I'll bring you more. Can I take some squares with me, and I'll bring you some? Thank you. I'll bring you some triangles, and I'll bring you some triangles. I'll take all this, okay? Because you have some there. Oh, I like that.
What do you want us to do again? I'm sorry.
So the instruction is, let's try to find patterns or vertices where we can find polygons whose internal angles add up to 360, right? So basically what I want is for us to find patterns that will have no empty spaces. Okay? What is that pattern? Yeah, write it down. So what is the pattern at the vertex?
It would be 3, 3, 3, 3, 6.
Correct. It's 3, 3, 3, 3, 6, right? Could you make it grow?
Yes,
Let's
if
see.
I had more triangles.
Maybe you can share. Okay, so let me write it down because you were the one that discovered it. How is it again?
3, 3, 3, 6.
What's your name? Ali? A-L-L-Y?
A-L-I.
A-L-I. Like that? Awesome. We get to put your name next to it because you discovered it. Well, hurry up. You have to claim the pattern. If you claim the pattern, I get to put your name next to it, and it's yours. You need one more square, right? Oh, you guys just have squares? Oh man, that's sad. Can you go and get some hexagons? I think they have some hexagons. Oh, that's nice. Look, independently. Working independently, you arrive to the same conclusion. All of you. That's super cool. Can someone tell me what the pattern is at the vertex? I couldn't hear you, but say it again. Just come and write it down. Yes. And these 3 groups found it independently at the same time. That's pretty cool. Has anyone found a different one?
I only have the 2 shapes.
Nice. Could you go and write it down, the pattern over there? What the pattern would be?
We've got 6, 3, 6, 3.
Write it down. And this one is different, actually.
6, 6, 6. Devil.
Write it down. Write it down. It's you the one that has to. I will not write it down. I'll not dare. I'll not dare. What do you have?
3, 6, 3, 6.
Is that one out there? No. Go and write it down. What do you guys have?
I'm sorry. Yeah, I don't.
No, come on, come on.
Can I take a retest?
I mean, it has to go there. Someone has to write it down. It does. It does. Do you want to go and write the pattern there? Thank you. See? Oh, no one has done this one. So you should go and write it down. Can you go and write it down, please? No one has it, so. And you should write your name next to it. I'm sorry that I just gave you squares. You know what? Since I see you, I'll let you guys take this, which I was not planning on giving to anyone. So.
You guys get all squares. You gotta say.
Oh. Go for it. It's not there. Can you write it down? That's important.
Just write the number. Oh, sorry.
Remember, if you want to say triangle, 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 triangle.
Also 6 days.
That's correct. You will write 3, 3, 3, 3, 3, 3. If the pattern is not out there, write your name next to it.
Are we just doing regular polygons or any polygon?
I just. That's correct. It's not regular. But I cheated because I just gave them squares, and I felt bad, you know.
Yeah.
So.
So, but I mean, on our patterns,
But
we only want to stick to
if
regulars.
you want, you can discover new ones with this one. I will
That's
not
fine, you
oppose.
don't care. All right.
I will not oppose.
You just put 4 there. Oh, you just put 4. Oh, all right. Thank you. Yeah. Time to do more.
Are there 3? I'm going to tell you this. There are still. Thank you so much. This one is the one you wrote, right? 3, 3, 3, 3, 3, 3. No. Oh, awesome. Thank you so much. We are doing right now just yes, convex, just convex. So thank you so much. Okay, so this is very, very interesting. I'm going to tell you one thing. There is still some missing. There are 2 missing, which are that you made with triangles and squares. So I'll give you 1 minute to find one that you can do triangles and squares. With triangles and squares. We don't have much time, so. Triangles and squares. I feel like you need squares to find it. Can I borrow some squares from you?
Sure.
Yeah. You found it? That's awesome. Can someone, they might be different, so. Can I see it?
Is this one? Or do it got spaces? Like, 'cause right here.
Yes, but finish it. There you go. Go and write it down because no one has it.
All right, thank you.
Okay, we found the missing one. Okay, so this is super interesting. Once you're done with that, I am very, very.
I think that's how it go, right?
I'll tell you. I'll tell you because you have it right. It goes like this. This one goes like 3, 4, 3, 4, 3.
Oh.
Okay?
All right.
Which is different to this. Thank you.
Right.
Okay, so I am going to ask about 2 just because I'm super curious about it. Who wrote this one?
I did.
Can you tell us about it?
I just did it because I have all the triangles and one of this.
But I'm really curious because look at this one. This one would mean that your vertex has a triangle, another triangle, another triangle,
Yeah.
another triangle, 1, 2, 3, 4, another triangle, right? And another triangle and another triangle. And if you see, each of these will have 60 degrees,
Yeah.
right? So what you're saying is you are adding 60 degrees. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
Right.
So you're saying that all of them come in the same vertex, which would mean that it would be, that vertex would have 60 degrees times 20. And that's way more than 360. Does that make sense? So for everyone that has triangles, try to put, what is the maximum amount of triangles that you can put in a vertex?
6.
6. Can someone do it? Can I borrow it? So what's your name?
Yalen.
Yalen. So Yalen was kind enough to get me the 6 triangles. And if you see, the max that you can put of triangles is 60. It's 6, sorry, right? You all can do that. And that's actually really important. It's going to be really important. So this one, we'll have to check later what you meant by this. But let's be careful with that because that's actually taking us to the next point, okay? Now, notice that what you did is you put things together so that they matched, right? Now, you had just 3 kinds of shapes. But now, let's look at the table. Could you predict a pattern that would work by looking at the table? Could you predict a pattern without having the shape? Could you predict a pattern that would work by looking at the table? Kyle.
Just any polygon with a number of sides with internal angles that are divisible by 360.
Do you have an
One polygon. Yeah, just a hexagon.
okay, a hexagon? Uh-huh. What else?
Just 3 hexagons.
Oh, so you say 3 hexagons.
Same polygon with internal angles that are divisible by
That's another really nice theorem. What Kyle is saying is, look, this one is if you multiply by 3, you get 360. So you know that you can put 3 of those and get 360. 4 is the same, just that what you do is you put 4 of them to get 360. So whenever you see one angle that is factor of 360, you know that you can put those together and get a pattern that will work. So in this case, 3, 3, 3, 3, 3, and 3. And those are the 3, and all of them are here. Alex gave us the 3, 3, 3, 3. The 4, 4, 4 is by Aubrey.
Oh, yeah.
And the other one, which is 6, 6, 6, someone gave it here and did not dare to write their name there. So, can anyone see another one that you can predict that will work? Yes?
12, 12, 3.
Oh, I like that. So 12, 12, 3. Why?
They all add the 360.
Oh, so this one is 150 plus 150 plus 60, and it's indeed 360, okay? So that's a candidate to work, right? What is another one that you see that can work, maybe? Maybe, say that again?
2, 6, and 2, 3.
6, 6, and 3, 3. Let's see at that. This is 120, this is 120, and this is 60 and 60, and that indeed gives you 360. So you got another one, right? So this is another tool where you can mix the intuition of having the shapes, and you can use what you deduce from your mathematics to discover new patterns and try them, right? So a way of investigating this would be the following. A way of investigating this would be, okay, let's see which one add up to 360, right? And let's rule out the ones that are not. Right now, as it is, it looks like a really difficult problem because you have infinitely many polygons, and you have just a bunch of possibilities. So let's try to make it finite and attainable to end the talk, okay? So that you can go home and sit down and do research, because that's the idea of this, to send you home with a lot of questions that you can sit and discover, okay? So let's go back to the things that we noticed here, okay? We said 3 things. The first one was that there was not shifting. Actually, I'm not saying them in order, but there was not shifting. The other one was that they had to add up to 360, right? At each vertex, the polygons had to add up to 360. And the other one, which this one doesn't satisfy, was that we were interested to find the same pattern everywhere, right? So we're going to define, for our purposes of investigation, You can define it in a different way. But for our purposes of investigation, we are going to define a mosaic in that way. We are going to say, OK, so a mosaic is going to be made out of regular polygons, all of the same side. We are going to say there's not shifting, right? All of them match. If they match on a side, they match completely on that side. Then we'll find the same pattern at each vertex. So in our definition, that one there is not a mosaic because we could find two different patterns. And the last one is that at each vertex, the polygons add 360, which is no empty spaces. OK? So let's make it more attainable, and then you go home and you try to investigate more about this. What is the maximum amount of polygons that I can use in my pattern? Who can tell me? Tell me why, Ali. Ali, right? So Ali said 6. Tell me why. The answer is correct. It's perfect, actually. Who can help Ali?
360 divided by 60 is 6.
So, Leah?
Yes.
Wow, good. So Leah said, look, 360 divided by 6 is 60. 360 divided by 60 is 6. So if you think of taking the smaller polygon possible, which is the triangle, right? We just noticed that the most that we can put was 6 of them, right? There's nothing smaller than that. So if we put a square, well, it has to be less than that. It has to be less than 6, right? So we just proved with this that the max number of polygons is 6, okay? And then your problem, where you could use any amount, becomes something finite, because you have that this one, 3, 3, 3, 3, 3, is the max amount of numbers. So where does the investigation go from here? And it goes home with you because we don't have more time. But where does the investigation go from here? The investigation can go, OK, so now let's find out which ones are the ones that we can do with 5 polygons, right? And do you guys think, let's do this as our last proof or argument. Could I get, with 5 polygons, could I get to not use triangles? Could I have polygons that are not triangles if I have 5 numerals? It's the last question, and then we get to eat cookies and go home. Well, think about this. If we don't use triangles, the minimum that we can use is squares, right? So the minimum that this could be is 4, 4, 4, 4, 4, right? So the minimum sum of angles for this will be 4 times 90. And that's, 5 times 90. And that's definitely larger than 360. So I need to have a triangle at least. Now, could I have triangles and then just squares?
No.
Why not?
Because 4 times 90 is going to be
4 times 90 plus 60. So I need to have at least 2 triangles, right?
Yeah.
And then could I have 3 triangles? Three squares?
No.
Why not?
Because the sum of the interior angles of the squares is still going to be big.
Right, this is going to be 120, and this is going to be 90 times 3, which is 270, right? So again, it's impossible. So just by doing this exercise, by looking at the angles and how big, how small you can do it, you know that if you have 5 numerals, you need to have 3 triangles. So there you go. The only thing that you have to do is, okay, so I have 3 triangles which are going to add up to 180, plus 2 that I can go and look up in my table. That should add 360. And then by doing that investigation, you can find all the ones that have 5 numerals. Now you can go home and try to find the ones that do 4 numerals, 2 numerals, and maybe 1 numeral. One last comment is that was the definition that I chose, but more investigation, and that's how research in mathematics happen, can be born if you dare to challenge that. So for example, Javier, I don't want to do regular polygons. I want to do these things here. Then a new research project begins because now you have different angles. Javier, what if I do, instead of 360, that they add up to less than 360, and then what is born is objects that look like this. Okay? So the idea here is change your definitions, change what you are trying to investigate, and discover new worlds. Okay? So thank you so much.